It's my pleasure to introduce Steve Feldman. Yes.
Oh dear. All right, let's see if this technology works today. Okay. All right, I'm here to actually talk about something a little different instead of my usual May East, May West topology speech, which I'm sure most of you have heard a couple thousand times already. I'm going to talk about an experiment that I've been trying. Basically, I got the weird idea of what would happen if we tried to build an exchange point out of MPLS, prompted, of course, by some of the MPLS router vendors who said, wouldn't it be really great if you built an exchange point out of our equipment instead of what you're using now? So to start, let me set a context here. This talk is the result of some testing I've done in the lab. Unfortunately, not nearly enough testing in the lab because I only got the equipment a couple of weeks ago. So there'll be a whole section at the end of stuff that I still have to explore. So please don't beat me up for the stuff I haven't done yet. It's not because I didn't want to. This is kind of a feasibility proof of concept type thing. There was no commitment on the part of MCI WorldCom or anybody else to make this into a product, just setting that straight up front. If it works, maybe someday, yeah, great. If it doesn't, oh well. That's what testing is all about. Okay, I'll start with the requirements. What we're trying to do to grow the maze. We figure we need support for gigabit speeds. Right now we can support OC12C with the existing maze. We need to go beyond that, obviously. Still needs to be at layer 2. I don't want to be taking people's BGP routing tables and screwing them up and nasty things like that. We need to be able to support remote connections. Co-location space, especially our co-location space, is finite, so we need to be able to support people coming in from other places. Typical exchange point security issues like we don't want provider A to dump traffic on provider B like it used to happen at the old 50 maze all the time. Point default at somebody and screw up everybody else. Along with that, oh dear, I can't spell. Bandwidth management, supposed to be management, means that we want to preserve the current PVC-like structure of the ATM MAE, where you can actually subscribe for a certain amount of bandwidth, be guaranteed it, and be policed on it too, so that you can limit how much somebody can send you. And yes, to the people who want to be able to do UBR best effort type stuff, yeah, that's a requirement too. Maybe we'll have it someday. And the last bullet, which we kind of learned, well, we knew it going in, but it's been obvious to us. We can't introduce a new technology without trying really, really hard to be interoperable with the stuff we have there before, that's been there before. We don't want to make everybody, if we can possibly avoid it, buy all new equipment to do this. MPLS satisfies a lot of those requirements. Let's see. Packet over SONET feature of MPLS is nice for us because it's where the router manufacturers seem to be devoting most of their development resources right now. We have OC48C, OC192C, even pause today. I haven't seen anybody build an NTM interface on a router with those speeds, certainly not in general deployment. And a nice side effect is you lose the cell tax. Another nice thing about MPLS is that it's a standard that's independent of the physical medium. So in theory, at least, you could have interoperability again between your POS and your ATM, and maybe even Ethernet variants, maybe even FIDI someday. So you could preserve your hardware investment. You still have to run MPLS encapsulation on it, but at least it's defined how to do that. And yeah, I know there's packet size issues and stuff, but that's for further away. Just to be complete, there are lots of alternatives to MPLS. One of them, of course, is ATM, like we're doing today. Problem with that is nobody, like I said, nobody's really building higher speed than OC12 router interfaces right now. Cell tax still doesn't go away, and we still haven't figured out a way to make it interoperate with the existing LAN technology. Frame relay pretty much has the same set of problems. It's nicer in a way than MPLS because it's simpler to configure currently. There's no layer 3 involvement, so you don't have to figure out how to make it deal with your routing tables, and I'll get to that later in the talk. And there's same interoperability issues. And also nobody really builds a real fast frame relay switch. Turns out you can take some of the existing MPLS LSRs and make them into frame relay switches by setting some configuration variables. I haven't tested that. It probably works, but haven't tried that yet. And of course, gigabit Ethernet, which a lot of people are doing right now. Gigabit Ethernet is probably the best choice for an environment where you're sitting in a large colo area and everybody's running wires across the room. It's harder if you have to bring in connections remotely, especially if you want to avoid things like net edges in the middle. It's not impossible because you can do things like run Gigi over dark fiber if you're in an environment where where it's possible to obtain the dark fiber to do that with. The bandwidth management stuff and security issues. There are enough hooks now in some of the newer switches that let you do some security and VLANs and stuff like that that will let you achieve sort of the same kinds of effects as you get now with ATM. So it's less of an issue than it was even a year ago. Anyway, I'm testing MPLS, so that's what I'm going to talk about for the rest of this presentation. The first test was to take the equipment I had and just try setting up MPLS to make sure I knew how to do it. The test environment here consists of 2 Juniper M40s and 1 Cisco 75 something, with one of the M40s set up as the exchange point switch and the other 2 routers set up as customer routers. You can't probably see down at the bottom, but there are loopback addresses on each of them, which are used to actually build the circuits. I'll show you that in the configuration. So the first test was really just to build LSPs between the 2 end customer routers and make sure you could actually do that, run an eBGP session across it and actually forward traffic across it. I mean, that's the kind of thing that sounded obvious, like it ought to work, yeah, but had anybody ever tried it? Well, I was going to try it. So this is the boring part. The configuration on the Juniper peer router, basically I just set up an LSP to the Cisco peer on the other side with an explicit path. And I've turned off the constraint-based routing, and I'll get to the reasons for that in a moment. Also turned off decrement TTL on the grounds that, well, a couple of reasons for that actually, and we'll get into that now. One of them is I don't know that everybody needs to see what's happening in the middle of an exchange point, but the other and perhaps more important reason is that I don't want the routers in the middle of the exchange point to have defaults or to carry full BGP tables or anything like that. So if it did decrement TTL, a trace route, the ICMP TTL expired, would actually never make it back to the sender because it wouldn't have a route. So you'd end up as a missing hop in your trace route, and that's ugly. Anyway, so here's an explicit path that goes through the middle exchange router to the far side customer router. Here's the BGP configuration, just a simple BGP peering session to the other side. I actually did set multi-hop as part of the experimentation, and I never took it out to make sure that it still worked, and in fact I imagine it won't for reasons I'll get into again in a moment. And the addresses are set to the loopbacks on both of the peer routers. On the Cisco side, same basic thing. Set up a traffic engineering tunnel back to the Juniper. Put my thing here. Again, I used an explicit path going back. You notice here that there is no statement to turn off the constraint-based routing and no statement to turn off the TTL decrement. I wasn't able to find in the documentation any reference to the capability to do that. That doesn't mean it's not there, it just means I don't know how to do it. But the lack of those things does cause some problems, which I'll talk about in a moment. And finally, here's the configuration of the guy in the middle. All I'm really showing here is, oh no, this is the BGP configuration on the Cisco. Same kind of thing pointing back to the Juniper. Here's the exchange configuration. Not specifically, but there's no BGP configured on it. There's no default route on it. All it has is static /32s back to the loopback interfaces on the customer routers. Okay, so here's what happened when I did this. First problem I ran into, Cisco would not build the LSPs unless I had an IGP turned on. It wouldn't work with default routes. So I turned on ISIS and everything came up like it was supposed to. BGP session came up, and I was actually able to send packets across these things. I didn't show in my diagram, by the way, the test host sitting on the sides there, and the BGP routes that are installed and forwarded and all that. But anyway, I was able to pass traffic across this thing. It worked just fine. The only real problem I had was the missing hop that showed in the trace route because the Cisco didn't do the decrement, or did the decremental TTL when I didn't want it to. Okay, so now comes a more interesting test. One of the other constraints of the May service as it is now is we want our customers to be able to tell us when they should be able to communicate with each other. It's what we're doing right now with our peer maker software. Essentially, you tell it who you want to peer with, and if both parties agree, then the PVC gets set up on the ATM thing. We want to be able to do something similar here, mainly for security. I haven't found a good way yet with MPLS of having a router that's receiving an LSP RCP request to say, no, I don't want it. So right now, best way is to have something in the middle that'll do it. Juniper has a feature called Circuit Cross Connect, which essentially lets you splice LSPs together. So in this diagram, the two customer routers have built LSPs to the exchange LSR, and the exchange has built a cross connect between the two of them. So it essentially looks like one long LSP, but there's something in the middle that's controlling it. Here's the configuration on the Juniper side. It's just a simple one-hop LSP to the to the exchange router. Again, no decrement TTL, no CSPF. The magic here is that because the LSP terminates on the exchange router, there's no route to the far end peer, so you have to add that by hand, and that's what the install statement does. You need to have route to the next hop or BGP doesn't work. So this installs that when the LSP comes up. Similarly on the Cisco side, pretty much the same magic. Build a tunnel to the exchange router. I still need to do the explicit path, it turns out, or it doesn't work. At least I believe that's the case. And again, I set up a static route pointing to the real BGP peer, pointing to the tunnel, so that the BGP can pick it up as the next hop. And here's the magic on the exchange router. Here's building a connection. Basically what you're doing is you're splicing together the incoming connection with the outgoing one. And, oh, this is part of it. No, this is the part where I build the LSPs from the exchange router to the customer routers. And here's the part where I glue them together with the connections. The statement's called LSP switch. And basically you just tell it the name of the incoming LSP and the name of the outgoing one, and it glues them together. And you have to do it in each direction since LSPs are unidirectional. And here's what happened when I tried testing it. First thing that happened was my Juniper crashed. Fortunately, Juniper was giving us really good support, and within 2 days they had us a new version of code with their bug fixed. And got it up and running, and it immediately worked. Basically, as well as the previous case, same set of problems with the GTL document and all that, but traffic passed, BGP passed, and it did its thing. So that showed that the circuit cross connect actually will do what I wanted to do in this case. Okay, here's some of the things I didn't get to test. If only there were a few more 100 hours in a day, I could have done some of this. ATM, really would like to be able to make this work with our existing ATM environment. We have some ATM interfaces on both sets of routers. I just never had a chance to hook them up and see what would happen. I do know that at this point, at least Juniper has a somewhat pre-standard ATM implementation, so it's not clear that it would work right today, but it will at some point. I haven't been able to try it yet with more than 2 peers. There's no reason why that shouldn't work, but got to make sure. Also haven't been able to try it yet with more than 1 NSR in the core. At this point, that would be not as easy for me to test since I only have the 2 Junipers. And Cisco doesn't appear to have a circuit cross connect like feature yet, at least again in the documentation that I can find. I'd love to test performance and see if you can actually pass more than 1 packet per second like a ping does. One problem I did run into was the way I had it configured. Ended up setting addresses on each side of the point-to-point circuits between the customer routers and the switch exchange router. So that consumed up a /30 for each one of those, in addition to the address that's consumed for the loopbacks. I'd like to try to find a way to reduce or eliminate that, so we don't need to eat up as much address space in building one of these. And the other thing that would be interesting, and that's much further down the road, in my mind at least, is building an exchange where you can actually have LSPs, true inter-provider LSPs essentially. They originate somewhere in one provider's backbone and terminate somewhere in the other provider's backbone. And we're just passing transparent PVC-like things in that case. Those are things that I test. So here's some preliminary conclusions. It's not quite yet ready for prime time, mainly because of these little features that aren't quite implemented there, or if they are, I didn't find them in the documentation. Right now, the implementations that are there are tied really to the application of traffic engineering, which is where the demand is certainly. And the fact that I was able to tweak it to make it do what I wanted was pretty good, but there are still a few more knobs needed, especially on the Cisco side, to make it really do what I want. But it has potential. I think all those things that need doing are really just a matter of somebody sitting down and writing the code to do it and telling me how it works, and it could work. So the results of the test so far are a qualified success, which I think are capable of doing quite a bit better. I think this could be quite a viable product. Of course, like I said, I can't guarantee we'll do this at any time, but it's nice to know that we could. Just a couple words of thanks to Juniper Networks for lending us the M40s and for their really fast response when I found the bug with the cross-connect, and also to Cisco Systems, which offered a lot of support and offered to lend us some equipment, but it turned out we already had what we needed in the lab. And finally, here's my contact information, usual. This presentation will be up on the web shortly after I'm done up here. Any questions?
I have one,
Okay.
but I'm going to ask it up there.
Okay.
Your last content slide made the assumption that the MPLS could either be used for TE purposes or for the purpose that you were using it. Why don't you call what you were doing TE?
It's really, in a sense, it's TE, but it's layer 2 TE, maybe. Let's try to put this into words. The purpose of traffic engineering, as defined in these implementations right now, is basically IGP shortcuts. So within the interior of a provider's network, you can get from point A to point B over a traffic engineered circuit. I want to be able to do the same thing that's outside the IGP domain. And that's really where the tweaks have to happen, is decoupling a little bit more the IGP from the LSP setup. So you can still call it traffic engineering, but it's slightly different from what the vendors are calling traffic engineering right now.
Steve, thank you.
Thanks.